Okay, now if we want to estimate the area under the curve, it helps to go ahead and draw the region under the curve. Here's a region, and we can shade that with some kind of a pretty color. See, there's not much out here. Most of it's in here, okay. And then we can say, okay, well, let's just do an estimate here, okay? Now from here all the way over to here, and that's bounded by the purple rectangle. We've got 0.09 newtons times 1 meter, right? So purple area is 0.09 newtons times meters, which is 0.09, of course, joules, which is what we hope because we're trying to estimate work, right?
Right. Okay.
Okay.
We did that wrong.
Yeah,
We made a triangle from the top of the curve to the 1 meter
Well,
point.
that's not wrong. That's
Yeah.
just another way of doing it, right?
Yeah.
Okay.
Now, if you want to do the triangle,
That's why we
from
said
here to here,
that's why we said a
it would
4.
be 0.045 joules, right?
Yeah.
And then you'd say, well, we take off this area, maybe it's 0.04, right? Okay? It'd be 0.0405. And that's easy to calculate. Okay? So I probably did it wrong. You can check me on that. Now, okay? But just compared to the purple, okay, well, you said you had 1/4 of the area of the triangle, right?
Yeah.
So that'd be like a 16th of the area of the rectangle. We don't want to divide 0.09 by 16. Just divide it by 10 and say, somewhat less than 0.009, right? Okay? That make sense? Pupil area, purple area, darn it. Okay? That is not 001. Mess everything up. Now I could write 0.009, but I'm just going to say 0.01 joule because everything we're doing is very approximate, right? Now if we calculate the actual area and find that it's 486 joules, we know that something is wrong with our estimate or something is wrong with our integral, right? Now, if it comes out 0.005 or 0.02 joules, we're not going to be too awful surprised, right?
Right.
If it varies from this by a factor of 2 or even 3, we'd say, okay, I just made a bad estimate, and then maybe try to reconcile it, right? Okay, well, let's go ahead and now figure out what to do for the integral. Now, you should go through the reasoning why the integral works. If you have this curve here, and I drew it more like a parabola than like a reciprocal square now, because I've been careless, but yeah, just a representation of the curve. We can take a typical increment here and approximate its area by taking a sample point somewhere within the increment. And here is the value of our function at that point, right? Okay? This coordinate, this direction measures force. This direction measures displacement. So on this increment, the area of that little increment would be the work done on that, the approximate work done on that little region, right? And I think I asked you, no, we're doing something very much like this. No, maybe I did. I think I asked you to do a 4 trapezoid approximation. Did I? Well, we probably haven't gotten there yet. No, that's probably something I asked the applied calculus class to do. I don't remember.
Okay.
I did all this morning. So anyhow, yeah, we're working more with breaking things into trapezoids there. Okay, but here we understand that your typical increment there
Left and right. Left and right.
your area would be f of r star delta r, where r star is your sample value, right? So, and this would representing make that a longer E, representing, okay? Representing, no, I gotta have an SE in there. This is gonna be a real mess. Okay, I gotta have an E here, just a little one. Representing, I do know how to spell. Okay, and I can usually spell and do math at the same time. Who knows what's going on? Okay, so we have f of r star delta r, right? And that represents force versus displacement, which is work, right? So total work is the sum of all your f of r star delta r's, and of course you can form a Riemann sum and use subscripts and so forth, and everybody knows how to do that. Okay? And that approach is an integral. Well, this is a sum over partition from 0.1 meter to 1 meter. So the integral will go from 0.1 meter to 1 meter. And now we know what to integrate to get the exact value, so go ahead and do it.